Okay, welcome back, everybody. My name is Tyson Oxer, Oklahoma State. If I haven't met you yet, I look forward to meeting you. Great to be here in person. Great for Stephen and Mike and Maria and everybody that worked to put this thing together. And so we have a good series of talks coming up here for this session. We're just hearing about flood forecasting. So we're going to switch to drought.
The microphone is on the computer.
Sorry. Thank you, Mike. So we're switching to drought here. And so our first speaker in this session will be Trent Ford. And so now at Illinois State Water Survey, University of Illinois. So Trent, I'll turn it over to you.
Yeah, thank you, Tyson. Last time I presented at it takes every inch of my being, I have to say moist. But at this workshop, I'm going to try to admit people as I get going if I can. I was at Southern Illinois University. I've migrated north to Champaign since then, although that was almost 3 years ago. This is what COVID happens. Today, I want to talk about flash drought, early warning. A little bit of research presentation here, a little bit of my soapbox about throwing in more soil moisture information when we talk about flash drought early warning. So we're going to try to do both of that. There we go. Oh, one too far. There we go. Okay, so I'm taking a figure from Jason Atkins' paper in 2018 that kind of shows the progression of what flash drought, how it occurs. And this is, of course, a conceptual model of flash drought. Every flash drought event is different. This is just one kind of summation of what that looks like. Although I will say that when we had a flash drought event in Eastern Illinois, Western Indiana this summer, it really progressed this way in an amazing way. For those who have somehow been able to avoid the idea of flash drought or learning about flash drought over the last 10 years, what it really is a drought that onsets or intensifies more rapidly than we think of. It's much different than flash flood, right? It doesn't come on in a matter of hours. Hopefully we'll never have drought like that. It also doesn't go away rather quickly because remember, we need to have the flash, but we also need to have the drought. So we need to have a below normal amount of either rainfall, water balance for a sufficient amount of time to make impacts, which means that, yes, a flash drought may come on in a matter of 3 to 8 weeks, where you go from near normal conditions, everything looks good, to not good, but it has to persist for enough time to really have impacts. So usually, when we kind of try to summarize across diverse climates, different sectors, although I will say flash drought really disproportionately affects agriculture and ecology more than water resources in general. The typical requirements for flash drought: we need precipitation deficit. Of course, I mean, that's necessary in any drought. But the thing about flash drought is that we really need to have a long enough period of precipitation deficit, but not so intense that we have that kind of typical glide down to drought. So at the time that we have precipitation deficit, the perception on the ground from different, maybe it's farmers, natural resource managers, has to be, yeah, things look okay, even though we've been drier than normal for a month or 2 months. Then what we have is a relatively short period of time with elevated evaporative demand. Higher temperatures, sunny skies, lots of solar radiation coming in, wind, lots and lots of evaporative demand and evaporation, pulling moisture from that soil, causing plants to transpire. And then we have that dramatic decrease in soil moisture. And that's really where the meteorology hits the ground. And that's really where we begin to see the impacts. If soil moisture declines quickly enough and sufficiently enough to restrict water access for plants, combined with that heat, which, even with adequate moisture, some species of plants will close their stomata anyway. When we have high vapor pressure deficit, we get vegetation impacts. So this is kind of the progression of flash drought. When we think about monitoring and early warning of flash drought, those are two different things, although they kind of meld together. My thinking is that, sorry, there's either a delay or I need to hit this again. No, I need to hit it again. Oh, this clicker, yep, I'm gonna double fisted here. All right, that really we transition from early warning to monitoring somewhere around here, right? If we use vegetation and agriculture impacts to provide early warning of flash drought, we're kind of missing the bar there, right? Because the impacts have already occurred. And so it's really this where we have the meteorology as well as the decrease in soil moisture, where we transition from providing early warning to monitoring what the conditions are like on the ground. There, let's do it that way. So we have a lot of different data sets that, you know, with the kind of advent of studies about flash drought, we've had these different data sets that have been developed for monitoring and then for early warning, right? And those two terms are used interchangeably. But again, the idea here is monitoring is what are conditions like right now? Think about the US drought monitor, right, which doesn't provide early warning or forecasting. It's a monitor of what conditions are like on the ground. And then we have early warning, which is more of a kind of an outlook, not necessarily a prediction or forecast, but an outlook of what we're looking at. So for monitoring, we have the evaporative demand drought index, or EDDI, which is based off of, as the name kind of represents, evaporative demand. And again, it maybe can be used for early warning, although I wouldn't say it's necessarily the best product for that because it's updated weekly and it's past looking. Here are what conditions are like right now. But it is really important because it does give us a snapshot of, okay, here's what evaporative demand has looked like in the recent week or month or season. And that can give us an idea for, okay, how much demand have we actually had, which of course is a really critical variable for flash drought, right? Because flash drought does not occur with precipitation alone. I will die on that hill. You really need that evaporative demand. The standardized evaporative stress ratio is another really important monitoring based off of, again, evaporative demand and ET. And then we have quick dry, which is a proprietary blend of all sorts of different indicators that combines into one that can, again, provide some early warning, but it's past looking. It says these are the conditions that we've had over the last week or so. Then we have early warning, tools that are specifically made for early warning. One is the flash drought assessment using SMAP hydrology. That's called FLASH. And what FLASH is as it mentions, it uses SMAP soil moisture, surface-based soil moisture, to provide sort of a, here's what conditions have looked like recently for soil moisture, right? Kind of trying to capture that decline of soil moisture, which is really important. Because if we're just using meteorology to provide early warning for flash drought, we're missing that soil moisture component, right? So for example, maybe this hypothetical example where the next 2 weeks looks fairly dry, fairly warm, right? Well, in parts of Illinois, if that were to be the case, parts of Illinois have gotten 14 inches of rain in 3 days. That's probably not going to be an issue, right? Our soils are saturated, if not above that. So it's not the meteorology that's really going to cause a problem. It's really looking at the soil moisture decline to give us, okay, if our soils are at that point where a 1 to 2 week period of dry and warm weather will cause problems, that's really where we're going to be able to see the flash drought potential. The other side is the meteorology. This is Beth sitting here, the Midwest Regional Climate Center's flash drought risk tool, which uses a machine learning blend of multiple meteorological variables. You tell me if I'm explaining this wrong, and provides a probabilistic outlook based on GFS forecasts that are initialized every 6 hours. So it's really high resolution of where it seems like the meteorological conditions are advantageous for flash drought. This was, I think I snapped this a couple of days ago, and you can see obviously, you know, this area is in drought. And so the idea here is, and this is kind of the framework I'm trying to build, is that the ideal tools or suite of tools for early warning of flash drought would be something that can combine the advantages of both of these tools. One that has the forward-looking forecasting component, because we need to know for early warning what's going to happen in the next couple of weeks. And we're really talking 2 to 4 weeks here. And you can't give farmers, ranchers a 5 to 7 day heads up. Decisions don't get made on that time scale, right? They're 2 to 4 weeks at minimum. But at the same time, we can't rely on forecasts alone because we need to know what conditions are like, right? I gave you that hypothetical situation of soils are just too wet. It doesn't matter how hot and dry it's going to be over the next 2 weeks. You can have the opposite concern where we're in drought, right? Now, if Jason Ackerman were in the audience, he would stand up, throw something at me and say, yes, but you can have flash intensification. At which point I would say, yeah, that's true, but those are two very different phenomena, two different processes. So what we're really looking at here is a way to try to provide early warning for moving from things are looking okay to into drought in a rather short period of time. And so to do that, the idea is to combine the near-term kind of early conditions of soil moisture with the near-term forecasts of what's on the horizon for weather. I'm gonna skip this slide because I've already gone too far or too slow here, but this is basically the goal of the project here. So this is what I have, what we've kind of done so far. It's a sort of a simplistic setup for a study. So what we're trying to do is we're using, again, the conditions on the ground right now, soil moisture wise. We started with NLS2 NOAA model. Although, as I mentioned in a little bit, we're going to transition to an observation-based product that Stephen and his team are putting out. But this is just the top 1 meter soil moisture. So basically, what are conditions like right now? And what have they been over the last maybe 2 to 3 weeks? You know, yeah. Oh, sorry. Yeah. I migrate with my, no, sorry, folks in computer world. So over the last 2 to 3 weeks, what have soil moisture conditions look like? And then for the forecast, okay, here we are right now. Here's what soil conditions look like. What are our weather forecasts looking in the next 2 to 4 weeks? We're using the CFS V2 GridMet product, which maybe 3 months ago I didn't know existed. Folks at DRI, as well as others, are basically what they're doing is they're taking the daily CFS V2 output, which is at a fairly coarse resolution. They're downscaling it to GridMet, which is a 4 kilometer spatial resolution, and also bias correcting it to the GridMet climatology. So what that means is you have a really long and high quality observation-based data set with which you can validate, provide real-time sort of verification of this. They have 20-member ensemble, and John Abatsoglu at UC Irvine was kind enough to provide hindcast for me back in 2011. So we really have, in this case for this study, about 11 years of data. That's the data that's available. Basically what we're doing is we're taking the change in soil moisture at up to 20 days prior to initialization, plus the current soil moisture anomaly of the last 7 days. Again, how has soil moisture changed recently? What's the anomaly of soil moisture? Combining that with 2 to 4 week forecasts of total precipitation and total PET, calculating anomalies. We've also thrown variables like minimum temperature, dew point temperature in there. And we're combining these two using a random forest prediction model, which is sort of machine learning. We've also did a multiple linear regression just to see Trent, the other Trent, which is nice to have another Trent in the audience since Trent Franz isn't here, to see what, model parsimony. If we can do what we want to do with multiple linear regression, why use random forest, right? That sort of thing, because it's a bit harder to interpret those results. This is kind of what we're seeing. So what I'm showing you here is a few maps of model performance for predicting dichotomous flash drought. Yes, flash drought occurred in 2 weeks. No, it didn't occur. Short validation period here. Again, 10 years, 10 or 11 years. Without soil moisture, just using the meteorology of the CFS forecast, this is our equitable threat score. It's a skill score. It's just one representation of skill of the models. And we can, the perfect skillful forecast will have one value of 1, just basically predicting climatology is a 0. So you can see here that we have fairly low values just using the meteorological predictions here. It doesn't vary a whole lot across the country. I'm just summarizing by NCA 5 region here. I think Aaron's probably got a twitch in his eye because he's seen these regions too much by putting together the Midwest chapter. But then when we include soil moisture, what we see is significant improvement in model performance, especially the Midwest, the Southeast, the Northwest. So these kind of more humid regions, that's where we see where including the current condition of soil moisture significantly improves that model performance. Now, why does that happen? The biggest reason is it dramatically cuts down on false alarm forecasts. So this is showing model bias, basically the ratio of how many flash droughts the model predicted versus how many actually occurred over that 11-year period. What this is showing is that for the Northern Plains region, the model predicted 10 times as many flash droughts as what actually occurred just using meteorology alone. And that's because, I mean, if anybody lives here in the plains, I don't know a lot of you do, or the Southwest, the weather that's conducive to flash drought happens a lot in the warm season, right? But the soil response may be a little more variable. You can see quite a bit less over forecasting here in the more humid regions. When we include soil moisture, yes, we still get over forecasting in these more arid regions, but it significantly cuts that down. Instead of having 10 times as many forecasted flash droughts as what actually happens, now we only have double. And here in the Midwest, it's right on par, as well as in the Northwest. We actually have a little under forecasting here in the Northeast. So again, including that soil moisture information really significantly brings a model closer to what's actually occurring. I'm going to skip this one. This is basically, again, showing the false alarm rate, which is, again, showing that idea of having way too many forecasted flash droughts just using meteorology alone. So summary here, and I will say, just as a point, We did do the same test, only just using soil moisture, like the recent soil moisture trend, not using the meteorology, and the results were also very poor. So again, what this is suggesting is the combination of the two that really achieves the optimal results, at least, well, I should say, especially in those more humid regions. So a couple of summary things here. I don't necessarily want to read this slide, especially because I'm probably running out of time here. The next steps are really probably the most important things. You know, we're going to try to improve the meteorological predictors. It's a pretty simplistic random forest model using only 2 variables. That's something that we want to do. Moving from model soil moisture to observations, Stephen and his team and Ileana have produced a 4-kilometer scale observation-based grids from nationalsoilmoisture.com. I'm really excited to plug those in and move away from NLDAS for finally. And then also thinking about flash drought early warning. What I'm not proposing here is you should use my product, right? Use my tool. Everybody use my tool. It's the best tool. What I'm trying to show here more than that is that there are multiple different advantages for different tools when it comes to flash drought in different places. And so really importantly, that when we think about a flash drought early warning system nationally, we really not be thinking about one product, but a suite of products that we use in different ways in different places to capture, to perform the best. So my information, my contact information is up here, and then acknowledgements, including Marina. Thank you very much for your input on everything, and I'm happy to take any questions. So thank you. Dave, do you have time?
Yeah.
Okay.
So I'm wondering about something that has drought more associated with depth of soil moisture. From drought being indicated, if you're talking about vegetative response, to deep-rooted crops who are drawing their quite a bit of moisture from subsoil and below, versus drought at the times when you're more interested in the plow layer or areas that you're having germination trying to happen in there, and drought affecting a surface more. So rather than an aggregated 1 meter soil moisture thing, what are your thoughts about going to something more depth related?
Yeah, that would be ideal to test this sort of idea on different depths, multiple different depths of soil moisture. And certainly the 1 meter, I include the 1 meter because, you know, historically we've thought about just using the surface 0 to 5 or 10 centimeters. I think is just too shallow to include. But the kind of rooting zone, maybe down to 40 or 50 centimeters, would produce. I mean, it'd be interesting to look at those results as well as the 1 meter column, and they will probably tell us different things. Certainly, the top 50 centimeters is going to be a lot more dynamic. And so, you know, I know, at least in Illinois, that our, 100 centimeter soil moisture doesn't vary much at all. And by the time we see that really start to decline, we're in much worse drought than what we'd say agricultural drought. That's when we begin to see base flow really start to affect stream and water resources. So that's something that we want to do as well. And again, this is one of I kind of flew through the slide where I was kind of laying out the goals of the projects overall. But one of the big things at the bottom said, like, communication, effective communication. We can make the most accurate tool in the world, but if it's not actually targeted towards actual decision making, it's not going to do anything. So this is where having, if there's certain processes or decisions that need to be made that are more affected by superficial soil moisture versus deep layer soil moisture, then that's something that we should look at as well. So hopefully that answers the question.
Thank you.
Yeah, Peter.
So I'm just trying to make sense of why your results were the way they were in the West. Can you remind me what the verification condition was for if a flash drought did or did not occur?
Yeah, I didn't actually. I won't remind you because I didn't actually say it in the presentation. So basically, what we use for a flash drought is if it went from the climatological 40th percentile down to the 20th percentile in 6 or fewer pentads. So basically 30 days, and stayed below that, at or below that 20th percentile for at least 4 pentads.
Okay.
So it's sort of pulling from a couple of different definitions, and certainly the sensitivity to the definition of flash drought is something that we'll need to test. But that's sort of starting with what has been accepted by a lot of previous research, and then kind of moving out from there. And certainly it'll be interesting when we do the sensitivity to see how the regional statistics may or may not change. Yeah, Brianna?
So really interesting. My question sort of actually is closely related to Peter's. So you take sort of a quantifiable definition of flash drought. I'm just curious, do you think that might vary by region? Because these regions are really different from one another.
I think it'll vary by sector. And that'll inherently vary by region. So, and the time scales will also vary quite a bit too. I don't think I know it's not a coincidence that the model that I developed in my office in Champaign, Illinois performs the best in the Midwest. That's right. My perspective is shaped by where I live, right? And so what flash drought means to the desert Southwest or the Southern Plains can be different. So that's something that is also has to be taken into account, which also leads to my points that a flash drought early warning system is not going to be a product, right? There's heated arguments whether or not the U.S. Drought Monitor can even properly represent drought across all these regions, let alone like flash drought. So your point's well taken. Thank you again.
Okay, thank you. Great. So a great lead in for Ronnie's talk. So next speaker is Ronnie Leeper, and we'll be addressing soil moisture under extreme conditions, including drought.
Yes.
Okay, perfect. All right, take it away, Ronnie.
All right. Well, good morning. I want to thank the organizers for putting this together and getting us in person again. Glad to see faces in a room instead of being in my PJs on a call. I also want to thank my co-authors, Mike Pilecki from NOAA, and then also a student, Matthew Watts, who really kind of spearheaded and got this project going. And we're going to be looking at satellite soil moisture and how well it can detect extreme conditions. Some motivation for the study. I think everyone in the room and probably even on the calls understand the value of soil moisture and how it could be used to help monitor floods and droughts and everything in between and help people make decisions. So I don't want to spend too much time on this. There's a lot of great talks. Trent just shared some on how these data can be useful to help people make those decisions. And so we'll be hearing more about that over the next couple of days. We played around with various different satellite products. So we looked at AMSARI-2, we looked at SMOS and SMAP. And regardless of what satellite product we chose, we realized eventually the satellites are going to come out of the sky. If we choose more modern satellites like SMAP, you might be missing historical references like the 2012 drought. And so that led us to the European Space Agency data set. This is a harmonized data set where they've taken all the satellites that monitor soil moisture conditions since the beginning of time, if you will, since the late 1970s, and they've put them together. So they have two products that we're interested in, the combined product where they've taken the passive and the active satellites, the red and blue, and combined them into one product. And then we're also going to be looking at the passive products, which are the satellites in red there. This provides only surface soil moisture conditions, so we're not getting the deeper depths. It is on a 25-kilometer spatial resolution, and it's provided once daily. So the goal of this project is to assess how the European Space Agency's combined and passive products are able to detect soil moisture extremes at CRN locations. I got maps of Alaska and Hawaii there just to show you where our stations are, but we're going to be focusing on the CONUS. We don't have too many sensors monitoring soil moisture in those locations. We're focused on the growing season, so this will be March through September, and our period of record is going to match the CRN as much as possible, 2010 to 2019. So we're going to be ignoring those earlier data sets, at least for now. And we're going to be looking at how well it captures the volumetric variations, but also standardized soil moisture. To standardize the satellite data, we essentially took the nearest pixel to every CRN site. We extracted all the data, so we didn't account for any sort of regional area averages to point measurements. And then we used the same approach. We standardized the CRN soil moisture. So if you picked your day of interest, you go 15 days on either side. This gives you a 31-day window. You collect those for every year you have data, and you compute the median and interquartile range. And this allows you to compute standardized anomalies or standardized departures from normal. We excluded CRN sites if the satellite pixel had more than 40% of the measurements missing. So this took us from roughly 114 stations down to 87. These are mostly along waterways or large bodies of water where the satellite kind of detected water mostly over their area. So get into some of the results. This first graph here on the bottom left This is showing daily soil moisture observations from the US Syrian in black. It's kind of a histogram. We also have the passive product in dark green and the combined product in orange. Oh, I'm on the,
Just trying to knock out that.
oh, the thing up top. Gotcha. Thank you. I'm focusing on my slides and not what you guys are seeing. So one of the things that jumps out at me when I look at this graph is on the far left, Syrian has many, many more zero observations or observations near zero than the satellite's detecting. So if we're looking at really extreme dry conditions for like drought, for instance, the satellite's going to provide you a wet bias. If you looked at the combined product, it's also range limited on the wet side. It doesn't get many measurements above 0.4. And so when we dug into this, one of the things that we found is that the combined product is harmonized against NLDAS, it's PDF matched. And if you look at the field capacity of those measurements across the CONUS, very few of them are above 0.4. So that's why your range limited at 0.4. The passive product, on the other hand, is PDF matched to another satellite. And so you can get much wetter conditions or more frequent observations above 0.4. However, when we standardize them, when we use that 31-day window, we actually get very similar PDFs or histograms, if you will. So the power of standardization there. In this graph, I'm showing you on the top row is all the passive observations. The bottom row is the combined product. And we're looking at RMSE values for all observations on the far left. The extreme wet observations, so these in the middle, these are observations where CRN exceeded 0.5 standard deviations above normal or greater. And then we also have the extreme dry on the far right. These are observations or days when CRN was below negative 0.5 standard deviations or more. There's more colorful dots in the top panel. So that means the combined product has lower measures of RMSE than the passive product. If we do this for the standardized anomalies, we get more color shadings in both top and bottom. Darker colors indicate higher RMSE. And again, the combined product is slightly better than the passive from the standardized perspective. If you focused on the 7-day combined wet extreme at the bottom, we start to see a west kind of east difference in the RMSE. These standardized anomalies are a little bit higher over the western portion of the country. You see this also the case for a dry extreme and to some extent all observations. We also went through and looked at some anecdotal cases. This is the 2012 drought. And so you see a series of lines for different years. So we have 2011, this is pre-drought on the bottom left. Then we have 2012, these are all for March through September. And then we got the recovery year 2013. The CRN observations are in black again. And you see the passive product is much more in line with the CRN during leading up to and following the 2012 drought. These aren't stations across the CONUS, I should say. So these are just stations that were impacted by the 2012 drought. So they had to have 30 days or more below the negative 0.5 standard deviations below normal for the stations to be selected. However, when we go to the standardized space on the far right, we actually find that the passive product, if you focus on the latter part of 2012, the combined product is more similar to CRN, although both of them don't get as low as the CRN standardized anomalies were. We also looked at flooding. So this is actually the Missouri River Basin. These are all stations within the Missouri River Basin and within 100 kilometers of that boundary. So again, I'm showing 2018, 2019. When we update our analysis to include 2020, I'll have a third set of lines there. I haven't done that yet. In the flooding case, we actually see the volumetric data. The combined products more similar to CRN, and then in standardized space, both look really well. They capture the upward and downward movements of soil moisture for the wet case in 2019. So this tells us that the satellite is capturing the overall evolution pretty well for these two particular events. We did a more thorough analysis where we went through, we defined various thresholds for drought. So these are your negative anomalies and then also wet anomalies. And what we're looking at here is measures of sensitivity. So this is very analogous to taking a test. If you take yourself back to 3rd grade, maybe you got 10 questions right, or you get 9 questions out of 10 right, you get 0.9. That's what that's showing here. So if we choose the negative 0.5 anomaly threshold, this means roughly 43% of the time CRN dipped below that negative 0.5, the satellite matched. So it's not a very good score, right? If you brought that home to your parents, they'd be mad. One of the things though is as you reduce the magnitude of the extreme, as you go towards 0, sensitivity increases pretty good. We also see that with precision. Precision is a slightly different measure. So it's taking how many times did the satellite detect the extreme event and the CRN matched it. So this is, if you did 1 minus these values, it's a little bit higher. It's around 50, maybe 56%. If you did 1 minus that, that's the measure of false alarm. So the satellite's not throwing up a lot of false alarms. It's just not getting as extreme. So in summary, the standardized satellite products were able to capture the evolution of those anecdotal cases. We kind of want to explore that a little bit more to see if that's every event or just the extreme events. However, they're not able to capture the magnitude of the extreme. They tend to underestimate that. We also want to dig a little bit more into why we see higher RMSE values out west and not in the east. So it just may be regionally the satellites provide better measurements. And then we also want to dig into that 30-year period to see if a longer time period might improve our anomaly calculations. Our initial analysis suggests no, but we kind of want to explore that a little bit more. And with that, I think I'm going to end early. So hopefully you guys enjoyed the talk. Happy to answer any questions you may have. I'd like to saw him first. Yes.
I have to read a lengthy question.
Okay.
Recently, I'm using scan. This is from Yulong Shop. I'm using a scan and serum and 5 centimeter soil moisture observations to evaluate UFS prototype experiments. I also found model soil moisture is much better than the observations as presented here. My question is, how reliable are the observations from 0.02, 0.07, and some for many stations? How do you trust your observations? For the 20 centimeter observations, model results are much closer to the observation. So basically, the surface is not as reliable as the depth.
Gotcha.
And what is your feeling for accuracy through that column?
Okay. So a lot of things to unpack there. The satellite only provides an estimate near the surface. So that's why we focused on just the 5 centimeter comparison to the satellite data. The 5 centimeter definitely has a lot of variability. It's more responsive to rainfall. And therefore, if you're doing a point to area, there's probably larger offsets. That's why I think some of the sensitivity and precision measures may be kind of low, maybe lower than I would expect in those comparisons between extreme events. So that may just be a 0.2 pixel difference. In terms of trusting the in situ data, it's what I got. So I do tend to trust the in situ data maybe a little bit more than the satellite data, although I do understand the point that it may be more stable at the deeper depths, and therefore you're settling around maybe something closer to normal. I hope I answered the question well. Yes.
Really enjoyed the presentation and just seeing how to sort of standardize and compare and think about benchmarking satellites and observations. I was curious about the spatial patterns that showed up with east and west. Have you looked at all to see if land cover or the heterogeneity of land cover soils around the CRN stations, given that you have a larger pixel and
Yes.
point plays into the variations in skill score that you saw?
We haven't looked at that directly yet, but that's a really good point. So there may be locations you're saying where over the satellite footprint, maybe you're going from sand to some sort of sage or brush, and therefore there's differences and it's averaging over a point. Yes, that's probably a good point. So we can definitely take a look at that.
Yeah, just
Thank you.
because we're also thinking about land cover.
Yes.
And soil variations and how that plays in. So I think you have a data set that would be interesting to delve into that.
Yeah, and I do recall hearing that the satellites have a harder time over the desert Southwest and sandy regions. And so I'm wondering if some of the satellites that go into the European Space Agency data set has more biases than others. So how they manage that when they combine them. But yes, thank you. Yes.
I might add that just the terrain differences in the west, aspect differences driven by terrain. Really average those pixels out to something that may or may not even represent anything in your pixel. It represents something next to the pixel.
Gotcha. Oh, that's another good point as well. Thank you. Yes, sir.
Regarding the spatial scale differences between the stations and the satellite footprint,
Yes.
Kilometers,
Mhm.
and then the stations like point measurements. So would you expect
Yes, I do expect that. And I think that's why those measures of sensitivity and precision are kind of low. I think the CRN is measuring a point, so it has much more, I don't know what the right word is, but it could definitely get much wetter. So if you think of precipitation, right, at a point, and then you're trying to estimate satellite-based precipitation, we see a similar thing. It's underestimating the extremes. So one of the things we do want to do is try to partner with a more dense network. Maybe there's some mesonodes out there I can talk to kind of look at multiple stations within a grid cell to kind of get a sense of what that bias is. But yes, that's a good point. Yes, sir.
Other than spatial temporal, is that certain times of the year, the spatial extent of your precipitation has a smaller footprint than others. You have convective thunderstorms in the summer, which may not affect the entire grid cell, as opposed to a large synoptic storm, which does affect the entire grid cell. So I just wonder if there's any seasonality in the variation.
We did look at seasonality. I don't have any plots out there, just simply by month. And nationally, we didn't really see much of a difference, but you would expect, and we didn't break it apart between East and West. So the West has much more seasonal precipitation cycles, summer monsoon. In the West and in the eastern part of the United States, though, you do get these pop-up versus synoptic kind of events between summer and fall. Tosh, yes.
So denser networks, we did this twice with CRN,
Mhm.
where we had two stations. We deployed dense networks immediately in the kilometer around them
Okay.
to get at some of that micro meteorological scale. And then the time frame is we go, and the question is, how long do you need to measure at a location to get that temporal stability and reference point for a point measurement that's permanent, like a CRN, to the generic, to the overall spatial heterogeneity that exists. And that varies from 6 to 8 months to 2 years,
Yeah. Okay.
depending on location, I think. And we've looked at, and this is where, say, some raws or deployable networks could be used to enhance local stations to give an idea of how the local points may represent larger
Right.
spaces. RAWS is a Forest Service network that's deployable.
Is this the study you did with Jesse Bell?
Yeah.
Yep. Okay.
But that was only 2 locations.
Yeah, 2. Yeah, 9 kilometers, or did you guys get out to 15? One. You stuck to 1 kilometer. Okay, that's really high. Okay. All right. I think that's. Oh, yes.
Okay, thank you, Ronnie. Really good stuff. I wonder if you could just unpack. I'm really interested in the histograms there. And I wonder if you could.
You want to go
unpack
back
those a little bit.
here?
Yeah, so the histograms for the CRN there. So are there a lot of zero values, or are they between 0 and 0.05?
Yeah, they're between 0 and 0.05. So the way our package is together, there's a range on that. Yes.
Okay, so 0 to 0.05 is one of the most frequent observations. And where and when are those observations occurring? Can you
I haven't unpacked that, but I'm guessing it's somewhere in the desert Southwest. Yes.
So maybe some stations are reading in that range.
Yes.
Almost all the time.
Yeah, and I should say that we limited the stations from the full set down to 87 here. And then we've also removed days when one with the satellite measure was missing or the CRN was missing. So we had the same number of observations across all 3 platforms. And so maybe in the desert Southwest, you get less clouds and therefore you have more years of that data. We haven't really unpacked that yet.
Right.
What that filtering is doing, yes.
Yeah, it'd be really interesting to.
But yeah, I haven't even thought about that. Thank you. Did you have another follow-up? Or you good?
No, okay. It's really, yeah, it's really interesting. And in all these cases, you start comparing these different data sets, yeah, I think as you demonstrated, we maintain a healthy skepticism about all of them.
Right. You have to.
Yeah. Great.
Right.
Okay, anything else for Ronnie? All right, let's give him a hand. Okay, great. And so we're going to go back to the University of Illinois now. And our next speaker will be Yi Yang. Am I saying it correctly?
Yes.
Okay, great. Welcome. He'll be speaking to us. Getting now more down to a theoretical basis, which I think is always helpful. and looking at this idea of plant water use and its connections to soil moisture. So, all right, please go ahead.
My name is Yang. I'm a graduate student from University of Illinois, and thank you for giving me this opportunity to give this talk. My topic is on transpiration response to drought. And in this talk, I will introduce a unified framework to reconcile different theories of modeling transpiration response to drought. And in particular, we will look at three theories: the plant hydraulics, supply-demand balance, and the empirical soil water stress. And this work is quite abstract, so if I cause any confusions, welcome to chat to me after the talk. So I will first introduce the background, and then we'll look at the mathematical relationship between the three models, and then evaluate their similarities, differences, and convergence. And finally, we'll have a few case studies to illustrate when are the added complexity of the plant hydraulic model necessary. So the background part, this work is after, but we actually conceived this study with very practical reasons. The first is soil moisture ET relationship. Many people have tried to improve the estimation of soil moisture through the assimilation of evapotranspiration data, but it's very difficult because the relationship between the two variables are very complicated, and the relationship actually varies between different regions, and the coupling strength is different for different environmental conditions. And if you really want to improve the estimation of one variable through the additional information of the other, you need to improve the understanding of the relation between the two. And second, the water stress, water resources are limited, and the irrigation accounts for like 40% of total freshwater use. And so there's a trade-off between agricultural food production and conserving water use. So is it possible that we reduce irrigation water use while at the same time maintain food production? And to achieve this goal,
Could you speak in the microphone? I'm having a little hard time.
Okay.
You have very good English. I have a hard time hearing.
Oh, sorry.
Thank you.
Let's move this one a little closer so we can have both for the online and in person.
Okay. So sorry about that. Yeah. Okay. So so can we achieve the co-sustainability of food production and water resources? And to achieve that goal, we also need to improve our understanding of the plant water use and the stress. So a little bit of background information about plant water use and stress. So transpiration accounts for like 97% of plant water use. And water stress can be triggered by both atmospheric dryness or insufficient soil moisture. And in modern non-surface model or terrestrial biosphere models, the transpiration response to drought is constrained by stomata response to atmospheric conditions and soil plant hydraulic transport. The first mechanism, stomata response to atmospheric conditions, are usually well constrained and well understood. Under well water conditions, like you have the Burberry stomata conduction model, you have a lot of other models as well. But the soil plant hydraulic transport is less understood and is poorly constrained. It's got a lot of parameters, or you have a simple model, but the mechanistic representations are insufficient. And we call the constraint of soil plant hydraulic transport on transpiration as hydraulic constraint. And we refer the models of this process as hydraulic constraint model. So, so we will have three models in particular to study in this work. First, you have a very famous empirical soil water stress function, which is also known as the beta function. Basically, you calculate a scaling factor based on soil moisture and apply that scaling factor to transpiration to reduce it when soil is dry. And you also have the plant hydraulic model, which resolve the water flow from the soil to through the plant substrate all the way to the atmosphere. It's a mechanistic model, but it's got a lot of parameters and very difficult to constrain. And we also have the supply demand balance model. It's relatively less used, but it's got some popularity in crop model like I've seen. And the original ecosystem demography too also use it. So everyone will want a simple model, but also accurate. And the beta function model causes a lot of uncertainties. It's simple, but not reliable. And this one is complicated. It's accurate if you got the parameters right, but it's complicated. So can we just choose a model based on different environmental conditions with the necessary process and strip out those unnecessary process to make the model as simple as possible, yet still being accurate. So in this work, we will look at the relationship between the three models to see what are the relation between the full model and the simplified model. And second, we'll evaluate when are the added complexities of the plant hydraulic model really necessary for different environmental conditions. So these are the two questions. First, their relationship, and second, when are the added complexity necessary? And we will look at the mathematical relationship first. To evaluate their relationships, we first build a minimalist plant hydraulic model. It's got two segments, soil to leaf water transport driven by water potential gradient and the soil plant hydraulic conductance. And the leaf to atmosphere water transport, which is the transpiration driven by vapor pressure deficit. In this figure, we represent that as TWW, which is the well water transpiration, which means the transpiration when there's no water stress. And there's a scaling factor based on leaf water potential, and you will reduce the transpiration if the leaf water potential is low. And when soil dries down, the soil water potential declines and the leaf water potential will follow. So the transpiration reduces based on leaf water potential. And we have the beta function. Beta function works like this. You have a scaling factor based on soil moisture unknown, and you apply the scaling factor to reduce transpiration. There's no such thing as soil to leaf hydraulic transport. But if we really want to understand their relationship, we need to find an equivalent form of equivalent plant hydraulic form for the simplified beta function model. And to do that, we introduce a hypothetical soil to leaf hydraulic transport segment. And we will see what the segment will look like for beta function approach. So let's say you decrease the transpiration based on soil moisture alone. And in plant hydraulic model, the scaling factor is based on leaf water potential. And in beta function is based on soil water potential. If for some reason, the leaf water potential in equivalent form of beta, equivalent hydraulic form of beta function is equal to soil water potential, and the two scaling factors can be equivalent. The only condition that this can happen, leaf water potential equals soil water potential, is when the soil leaf hydraulic conductance is infinite. And in that case, these two the hydraulic conductance is infinite, so the gradient must be zero. So the two potentials are equal. So to summarize the relationship, we say the if in the plant hydraulic model, the soil to leaf hydraulic transport conductance is infinite, this model actually reduces to the beta function model. So that's their relationship. And we also have the supply demand balance model, but for the sake of time, I will directly give the conclusion for that model as well, but you I think you understand the principle. We just derive an equivalent form, hydraulic form for the simplified model. So for supply demand balance model, it's when the response function, the scaling factor, stomato response function is a step function. And in this case, the Planck hydraulic model reduces to the supply demand balance model. And so in the following section, we'll also be focusing on the comparison of these two. And usually in a typical hydraulic model, it's more complicated than the minimum model we just built. It's got usually it will have 3 segments: soil to xylem hydraulic transport, and xylem to leaf hydraulic transport, and finally the leaf transpiration. And in this case, we can generalize the relationship we derived to this more complex hydraulic model. In the previous slide, we showed that soil to leaf hydraulic transport is infinite. And to generalize to this case, we can make the 2 segments both infinite. And this in this case, the Planck hydraulic model will also reduce to the beta function model. And next, we will evaluate the differences, similarities, differences, and the convergence of the simplified model and the full model. So in this figure, we have a transpiration response of the 2 model. The solid curve represents Planck hydraulic model, and the dashed curve is beta function model, and horizontal axis soil moisture, and vertical axis transpiration. And different color means different well water transpiration, which means different atmospheric dryness, atmospheric transpiration demand. And you say from this figure that when soil moisture is very high, soil moisture is sufficient, there is an overestimation of beta function compared to the Planck hydraulic model. Because in Planck hydraulic model, even if you have a very sufficient soil water, the soil to water needs to be transported from soil to the leaf to be transpired. And the soil to leaf hydraulic transport capability could be limited, as we have said earlier. And that will cause the transpiration to decline if the atmosphere is super dry. But in beta function model, as we have seen, the hydraulic transport, the hydraulic conductance is infinite. So if the soil moisture condition is sufficient, you can always have a very sufficient water flux from the soil to the leaf. And the beta function can always reach the well water, the no stressed transpiration. And so this is their first difference. The overestimation of beta function caused by the lack of soil to leaf, which is the xylem hydraulic transport limitation. And the second difference is when the transpiration downregulation does occur, the beta function, you reduce transpiration based on soil moisture only. So it's a decoupled response, but in Planck hydraulic model, the atmospheric dryness and the soil water jointly control the transpiration stress. And so if you want to recover those missing process of the beta function, you can do the following numerical trick by applying a cap to the beta function to fix. This is the original beta, the dashed curve, and if you apply a cap, if you apply a cap, the overestimation problem can be fixed. And if you additionally apply a dynamic form, the decoupled response can also be fixed. So the main idea of this analysis is to help us understand the next analysis. When are the added complexities of hydraulic model necessary? Let's go back to the previous slides. We have already seen that under sufficient soil moisture, beta function can be overestimating transpiration. But what if you have like an environmental condition and the atmosphere is quite humid? The atmosphere is not very dry. In that case, the well water transpiration, which is the atmospheric demand, won't be very high. Let's say you only got like 200 or 150 well water transpiration instead of 300, instead of 300. And you look at the SIAM curve, the difference between the two models are actually minimal. So in that humid atmospheric conditions, this type of difference is not very important. And so the final section will have a few case studies to say when are the ideal compensation necessary. First, we have the NE3, US NE3 flag tower site, which is in Nebraska. And you have the soybean planted in 2012, and which is a drought year. But if you look at the soil moisture, besides the first one, except the first one, all other layers of soil moisture will not go down, go below 0.25, which means the soil moisture condition is actually sufficient in that site, even if in 2012, which is a drought year. And this figure we show this one, the top left one, the response of the two models with the parameters calibrated for USNE3. And you can say under well water conditions, the beta function severely overestimates the plant hydraulic model. And this figure is the difference between the two for different combination of soil moisture and the well water transpiration. And you can also say when soil moisture is about 0.25, which is sufficient, but transpiration demand is very high, the beta function severely overestimates the red color. And this one, which is very crucial, is the actual data distribution in that site, the soil water content and well water condition, the well water transpiration. And the idea is if you have a site, the two models diverge, but the data distribution in that site also concentrated in that area. The bias caused by the simplified model compared to the full model will be very severe. And you can see in this site, a lot of data distributed in the well water soil, but also very high atmospheric demand region. And the two models happen to diverge in that region. And if you combine the two figures, and a lot of area come from that region. So the conclusion for this site is, if you really want to the model the VVD stress in plants, you really need to consider the soil to leaf hydraulic transport limitation. And we also have another case study where I will give the conclusions. In the US ME2, which is the Ponderosa pine forest in Oregon, and the coupled response is really important for accurately quantifying the transpiration response to drought. So to summarize, I have three take-home message. First, the simplified models are special cases of the full plant hydraulic model. And second, their response differences can be attributed to certain mechanisms or the lack thereof. For example, the overestimation of beta function caused by the lack of xylem hydraulic transport limitation. And third, the importance of certain mechanism for simulating transpiration response to drought can be evaluated for different environmental conditions. So for every different environmental condition, you can choose the most appropriate model with the process, the representation as simple as possible, yet still be accurate. So I will stop here, and if you have any question, feel free to ask. Yes.
So you nicely demonstrated and compared the accuracy of these different methods for those who might want to make use of your findings. Is there a way to identify or predict based on the ecosystem or climatic region in advance which of these methods might perform best? Or is it really necessary to do the more detailed comparison that you did with the Ameriflex data to determine the biases and which approach is optimal? Or can you generalize from your specific cases to kind of for the United States or for other climatic regions, in this location, this approach is gonna be the optimal?
Oh, thank you. That's a very good question. So if you want to know exactly the difference between different models, you will need to know two sets of prior information. First is the environmental condition, which you can know that from the flag tower site or from satellite data, meteorological data. And secondly, you need to know the plant hydraulic traits. Different plants behave differently under drought. Crops, forests, grassland, they behave differently. So to know the exact difference, you will need to know the plant hydraulic traits and the environmental conditions. But I think this study can serve as you can use that in two ways. First, if you really know the conditions, you can diagnose the difference and choose the simpler one for operational use and get rid of those unnecessary process. Simpler is better. And second is, you can use it as a pre-diagnosis. Like you don't know exactly the environmental condition or the plant traits, but you can have an educated guess for every environmental condition. And in that case, you can apply the simplified model that you think is appropriate to estimate the most important parameters. Let's say, if you know in Midwestern regions, like in Illinois, the soil moisture is usually sufficient, but the VVD can go very high sometimes. And even if you don't have the exact plant traits, you can still apply the model without the rhizosphere limitation, because the soil moisture most of the time don't exert any control on the transpiration response. But the xylem conductance is important, so you can estimate the xylem conductance. Yeah.
Thank you. Yeah, I enjoyed your talk. I'm just curious to know about, so the functions that you're showing, are these modules or components of some larger model, some land surface model or hydrologic model?
The model alone, the beta function model, the supply demand balance model, and the plant hydraulic model, they can be used in any terrestrial biosphere or non-surface models. So it's not inherently bounded to any specific model. But in this study, the final section, the case study section, we use the NOMP model to calculate the well water transpiration. To calculate well water transpiration, you need to use the atmospheric conditions and use the boundary layer process and also the stomata conductance model under no stress. So, so to answer your questions, the stress model, hydraulic constraint model, can be used in any model. It's not inherently bounded to any specific model. But in this study, the final part, we use the NOMP non-surface model.
Yeah, thank you. And I have a follow-up question on that. So some models, when they implement functions like this, they apply them not to estimate transpiration here, as shown as energy flux, but to estimate a relative transpiration or a relative ET, whereas yours looks at the absolute value. And so I think, I guess, can you comment on why you chose to use the absolute value rather than a relative value?
Okay. So the purpose of this study is to compare the different hydraulic constraint models, plant hydraulics and beta function. And they are, as I have said, they are not bounded to any specific model. And in your case, if you use a model that calculates relative ET, I think can also find a way to evaluate what type of stress model, the hydraulic constraint components they use exactly, and feed that to the framework and compare that with the other model that I studied here. I think there should be a way. I have thought about this question. Some models, even some model like stomata optimization model, they couple the stress model with the stomata model implicitly. You can't separate them, but I think there's a way to still evaluate them. Okay.
So this is a combo of my question, online question, and it's for anybody in the room. When we talk about models in the bottom of a model, how dry do you go before you like turn off the mechanisms in that model? So wilting point, I mean, 0 is kind of absolute, but often you find 0. So some people use wilting point, 0.1. What is the common bottom end of a model? For your plant processes, is there a place where you turn off the plant processes?
I think it's unnecessary to do that. In this framework, let's say you take the beta function as an example. The beta factor actually decreases to 0 once your soil moisture is below the wilting point. And in the plant hydraulic model, that depends on the plant traits. If your root is very capable of taking water from the soil, and even if your soil moisture is very low, it can still take some water. But if your root is not very capable, it will stop. So that depends on the different models.
Okay, thank you. Great job.
Thank you.
So our next speaker will be Peter Goble, and it's just a nice kind of continuing this theme that which we heard even in Trent's talk in the first session and just now in Yi's talk, sort of which models are going to be most beneficial for particular applications. That's a very common theme. So.
Yep, thanks so much for having me here, and it's good to see you all again. So my name is Peter, and I'm with the Colorado Climate Center, which is the state climate office at Colorado State University. And today I'll be talking about which soil moisture models add value to a statistical stream flow or water supply forecast in Western Colorado. I should say that this research is not published or even complete yet. So the title of this talk really ought to be which soil moisture models add value to statistical stream flow forecast in Western Colorado, please help. So I don't have a conclusive answer to that question. I'll just put that up front. But this is a project that is ongoing and funded by NIDIS. So we definitely appreciate their support on this research. So this is definitely an important question. And I think this slide nicely underscores the motivation for this talk. So the water supply in Western Colorado is part of the whole Colorado River Basin system that's used by 40 million people. And you've probably seen a lot in the news that this is a supply that has been dwindling with time. And Western Colorado is where some of the most productive tributaries of the Colorado River Basin are. And in recent years, we've seen a bit of a mismatch between the snowpack that we've experienced and the stream flow that we get in the summer. And you may have heard the term from Mark Twain that in the West, whiskey's for drinking, water's for fighting over. We like to at least know how much we're fighting over. So you can see here that looking at the year 2021, our peak snowpack values in Western Colorado from snowpack telemetry sites are shown in the left hand of the figure, but then the water supply or the cumulative April through July stream flow totals are shown on the right-hand side of the figure. And there are a couple things I have to clarify here first. We don't expect these to vary at a one-to-one relationship necessarily. I like to use the analogy of a budget that the snowpack that we get throughout the winter and spring is kind of like our income. And the when you spend that income, first and foremost, that money has to go into paying the bills, which in this analogy would be like recharging soil moisture and groundwater. And then the spending money would be like your runoff that goes into the lakes, streams, and reservoirs. So you might imagine that if you only made 80% of your normal income, you don't have 80% of your normal spending money. And we do see that here, although the disproportionality you're seeing on the screen is greater than what we've seen in previous years. And while river forecasting entities like the Colorado Basin River Forecast Center and like the NRCS are aware of added complexities like dry antecedent soil moisture conditions that help to lead to this, they still, at least early on in the season, aired high in terms of how much we're forecasting. So are dry soils to blame? And if so, do we have the resources available to forecast soil moisture driven stream flow depletion? And if so, which tools help us the most? And maybe at the end of this, some of you have some suggestions for which tools we can test out in this framework. And then one thing that's become an important point that's really risen out of this research that I will be talking about more is what actually impacts the stream flows more: conditions after the time of peak snowpack, where we're used to looking at the statistical relationship between that peak snowpack and our yearly water supply, or is it the antecedent conditions? Is it the antecedent conditions or is it the subsequent conditions? And this slide is just to raise the point that the amount of soil moisture modeling resources we have available to us has increased exponentially over the last decade or so. And so we have all these tools available that may help with this problem. And so we want to try to vet some of those and see if they can add value to a stream flow forecast. And the examples on the screen here are just examples of data sets that we have played around with, but there's certainly plenty more that we could play around with. So how are we going to determine if these soil moisture models are adding value to a peak season stream flow forecast? Well, we're going to take the last 40 years of data and we're going to look at things kind of in the framework that an operational stream flow forecast entity would have to look at things. So we're going to take the data, all the data that are available at the beginning of the month each month, and use that data to try to make a stream flow forecast. And so for these operational entities, they have to release seasonal water supply forecasts on January 1st, February 1st, so on and so forth. Our verification data set, or the data set that we're going to try to get right, is the naturalized flow records from the US Bureau of Reclamation for years 1981 through 2020. And when I say naturalized flows, that just means that there's a lot of man-made diversions to these water supply watersheds that have to be accounted for. And so the US Bureau of Reclamation's naturalized flows are the estimation of how much stream flow would have gone by or would have gone by these gauges if there were no man-made diversions. Our predictor data sets, the most important ones are going to be the ones that have been used historically. So SNOTEL, water year-to-date precipitation, as well as current snowpack. And then for these later forecasts in the period, you're noticing that we're forecasting for April 1st through August stream flow. So if you're making a forecast on, say, June 1st, you're also going to use the stream flow that you know you've already had for, say, April through May. And then we're going to do several different iterations of this with different soil moisture models attached to it to see if the soil moisture models are adding skill to the stream flow forecasts. So we're going to do this with a random forest model, and Trent talked about this a little bit earlier. So in each case, what we're essentially doing is we're hindcasting a handful of years. So what we're doing is we're taking 70% of those 40 years and using that as a training data set to see, based on the inputs that we have, what would we expect the stream flows to be in the years that are out of sample. That way the answer is not implicit in the stats that we're using for the forecast. And then we're going to do this building regression trees, and we're going to do it for each basin, and we're going to repeat it 500 times for each basin using different sets of training and test data sets. So why random forest? Well, Trent was talking about this earlier. A random forest can get at a little bit more complex statistical relationships than just multiple linear regression. But if we go back to the idea of parsimony that we talked about this morning, honestly, multiple linear regression does pretty well. So it's possible that this is even a little bit over complex. Here's an example of standardized soil moisture anomalies from 4 of the soil moisture data sets that we used. So each panel shows a different basin, and each colored line shows a different model, with the x-axis being the water year and the y-axis being the standardized anomaly. I just bring this up because it shows that while there is a fair bit of covariance between these models, which we would expect, it also shows that they sometimes say different things. And that's exciting because we get to see who's more right or who's more wrong. Or maybe right and wrong is the wrong way to phrase it, but which is more helpful for this application in particular. And then just before we dive into some of the results, this is just looking at, if you were just looking at the soil moist antecedent soil conditions alone, before you add on the snowpack and precipitation, which obviously we know is important because that's what's been used historically, how much of the variance in runoff the following year do antecedent conditions the fall before explain? And we see that in general, these numbers are fairly small, which is not surprising since you would think you need to know the snowpack. But we do see that there are some statistically significant relationships, particularly for the San Juan Basin, and that the relationships aren't equal for every product. So that's interesting to keep in mind as we go into some of these other results. So this is a look at, if we throw all 4 of these models into the forecast, how good are we doing? And we there's a little bit to unpack here. So I'll start by just explaining the figures and the animations that you're looking at. So the top left animation is showing the average fraction of variance explained in April through August stream flow from the training data sets, forecasting for the target data sets for each month of the year. And then the lower left is showing the mean absolute error of those forecasts, and the colored lines are showing different basin results. And so as we would expect, the fraction of variance that we can explain goes up as we get more weather data into the models. So these forecasts, of course, are going to be more accurate as you go from January 1st, when you've only built maybe 40% of your snowpack, to April 1st, where you've built most of it, to July 1st, where you even know some stuff about the spring rain, and then know a little bit about how much stream flow you've seen so far. And then the animation on the right is showing the weights of how much the machine learning is using each of these, each of the input variables. And we can see in most cases, it fits really hard early in the season to water year-to-date precipitation, which makes sense. And as the snowpack accumulates, it uses the snowpack more. And then as you get into spring and summer, it fits to the stream flow that's already been observed, which makes sense. If you're trying to predict April through August stream flows on August 1st, you already have most of the cumulative flow. So you're going to do a good job. I guess we could just go through July, but you're going to do a good job even on July 1st using the flow that you already have. What this is begging to show that I haven't shown is how much does it differ based on the soil moisture inputs that you use? And the answer is not much. It's fairly statistically insignificant, at least so far, because the model fits so hard to water year-to-date precipitation early and stream flow late. So, even though we know that antecedent conditions matter, and in some cases have a statistically significant relationship on their own to end of season water supply, the model isn't using that data very heavily. Now, this is the last slide of results that I'm going to show. And basically all the shaded area on these plots is important, and I'll get to what all of it means. But even the white shaded area, the area kind of under that, these black curves for each basin, where again, each panel represents one basin, and we're looking at the x-axis being forecast date and the y-axis being fraction of variance explained in these forecasts. Basically, the area under that black line is the fraction of variance that we are explaining currently. So that's what we're already doing right. And then the blue line represents, well, how much of the variance could we explain if we didn't give the model the stream flow itself, but gave it the future weather for the rest of the season? How well could the forecast do? And you can see that those are quite high, over 80% of the variance explained. which makes sense. So the gray shaded area is basically the area that represents what could be gained by a perfect seasonal precipitation forecast. And so this is just one of many applications that shows the gap that's created by imperfect subseasonal to seasonal weather forecasting and how much work still needs to be done there. The area shaded in blue is where if maybe you had the right soil moisture data set or you had better information, you could close some of that gap. And so this kind of goes to show why this is such a hard problem, is that the blue area in many of these cases isn't actually that large. So we're already doing pretty well if we just know what the future weather will be. Our biggest errors in these forecasts are wet springs like 1995 or 2015. But there are many other errors, thank you. There are many other errors that could potentially be driving what's going on in this blue area, or that could be used to close that gap. So for instance, in Western Colorado, about 40% of our runoff comes from higher than the highest snowtell stations. So you would expect that there would be a good correlation between snowpack where the snowtells are and snowpack further up, but that's not always the case. For instance, the higher elevations do better in years with a lot of small storms, whereas the lower elevations do better in terms of percent of normal snowpack in years with a few really big storms. A couple other things that could be driving this error in the blue are things like error in the Bureau of Rec's naturalized stream flow records, or maybe we're just not sampling the right places. Maybe we need other weather variables in there other than just precipitation. So I know that the NRCS is investing a lot of money in installing soil moisture sensors at these snowtell stations. I haven't used them yet because they're at oldest, close to 20 years old. They're just a little bit too green for this application yet, but especially as the climate warms and kind of the relationship between snowpack and water supply changes, I'm hopeful that those will be useful, but it is a tough problem. So just a couple quick take-home messages. I would say, at least to this point, if we look at the whole data set, the 2020 and 2021 stream flow kind of busts where we had these really dry antecedent soil conditions prior to the onset of the snowpack season. They're more the exception than the rule in the data set. However, they are becoming more common, but we also see years where we have a wet spring and we under forecast the amount of stream flow. But soil moisture was the third most heavily weighted factor at best in these stream flow forecasts. I think that my biggest take home probably from this research so far, and hopefully there will be more, is just telling people not to take your eye off the ball after peak snowpack season or after April 1st, especially. You know, I saw headlines in the Denver Post or NPR or the nightly news all about blaming antecedent soil moisture conditions for how dry it was in 2020 and 2021 in terms of water supply. And yes, that's part of the story, but these were also historically dry Aprils after peak snowpack season and dry springs in general. And we have reason to believe that if you look at these years as a case study, that was a really big part of why the years underperformed, is what happened after peak snowpack. And then just in general, you know, physically antecedent soil moisture conditions definitely matter, but in this application, we're having a hard time teasing out additional skill, at least to this point. And there could be several reasons for that. It could be 40 years of data is still too small a sample, where maybe we have some anti-correlation going on between what is your antecedent soil condition and what is your peak snowpack in that year just by chance. And then, you know, we may not have deep enough measurements or deep enough model estimates, and the models may have foibles that present them from, or prevent them rather from filling as much of the blue areas as they could. But that's all I have, and I'm certainly happy to take any questions on this if we've got time. Yeah.
So I worked for 10 years in the Utah Snow Office, and we have an unusually long period of record, pretty unusually clean data set for the in-situ sensors. Our lead hydrologist was aggressively installing sensors as soon as the Stevens Hydro probe kind of became a thing in the 90s. So we've got a little bit more of a resource to work from in that way than the Colorado Hydrology Snowtail office. So Jordan Clayton and I have done some work with Adrian Harkle at looking at in situ measurements, not model measurements. And made some hay with that.
Yeah, and I've seen some of those papers where that was part of what encouraged this work, where I've seen that there is potential there, but then when applying it to Western Colorado, it's been more or less a null result to this point. And I've been in contact with the NRCS about this research, and they've kind of said that, like I've talked with Sean Fleming about this, and he's kind of said, well, yeah, that matches with what we've seen in Western Colorado, and it's just it's a tough region, I guess. Yeah.
Yeah, it's tough. Like the chicken and egg reference earlier today, we've had a hard time getting other snow offices to deploy the snow sensor because it's a lot more work.
Yeah.
We're really operations based. We're not a research entity. So it's a lot of work, and they don't have staff necessarily who understand soil horizonation and why something may be putting up from the bottom versus the top. So they write it off. Well, it's broken. Maybe not. Maybe it's a micro.
Yeah.
Topography issue or something. So yeah, we're trying to break those barriers down and get these sensors installed so we can build that POR to draw conclusions from. Yeah.
Thanks so much. Was there a question over here, someone?
I'm going, but do you think there's like a forecast of opportunity kind of situation with this, where we know certain conditions, either leading up to April 1st or after April 1st, that so much comes factor in more or less to the prediction? So it's not kind of an across the board situation where you use the same model and so much of the factor changes depending on pre-existing conditions. I know like severe weather, those kind of forecasts. There's an example, MJO is thrown in.
Yeah, that's a possibility. Maybe it's one of those things where we would want to kind of apply it to the model as a yes or no, like is it in the bottom quartile or even, bottom 10 percentile of soil moisture? Yes, turn that on and see what that does. Or maybe we could try just combining it with, first off, seeing what's the total volumetric water content in that column and combining that with the snowpack and just putting it in as one variable like snowpack plus SWE and seeing, SWE plus soil moisture rather, seeing how that works. Tyson?
Yeah, thanks, Peter. This is great. I think this is just the kind of work that is needed. So it's really good. I have a comment and a question.
Yeah.
I really like the concept of the forecast gap that you showed there.
Yeah.
I think that's helpful. It does seem to me like the actual size of that gap is dependent not only on the precip forecast skill, but it's also dependent on how you chose to represent the antecedent conditions. So it's not maybe an absolute gap.
Yeah, and if anything, that gap might be underdone a bit because that's just how much skill you would gain from a perfect precip forecast at those snowtail sites. So if you had a perfect temperature and precip forecast for the whole basin, maybe you could make even more hay with that. Yeah.
And so I guess the follow-up on that is, so you chose November 15th.
Yes.
For your initial conditions, and I just wondered why that date, and could you use modeled soil moisture for April 1st or March 1st or something?
Yeah, that's a really good question. So November 15th was chosen because that's kind of when we expect the snowpack to start building at high elevations. I think that you could use something like January 1st and get basically the same result. My wariness with using April 1st especially, or even March 1st to a point, is that
that may mislead you because it's often the years with low snowpack where it melts early. And if you have an early melt telling you that there's wet antecedent conditions, well, that's not actually antecedent conditions at that point. It's the current year's snowpack already melting into the soil. And so I don't want to capture that, but I think there may be value in pushing it a little bit further towards the start of the forecast period. Yeah.
Along those same lines, I guess there's no reason to pick a specific date that was there. If you're throwing it all in the rainforest, you can pick November 15th, January 15th.
So I'll give you the real reason behind the specific date is that's the date when we got the SAC model input from. So we have one date for that model. The rest of the models we can play around with. Yeah, absolutely. All right. Yeah, thanks.
Good. Great stuff. Okay. Okay, a great set of talks and great job, by the way, by all of the speakers, by leaving time for questions and stimulating a lot of discussion. So great job. I want to hand it over to Stephen or somebody that can give us instructions about lunch.
Important lunch. There is lunch and it's available for everyone. Thanks to our friends at Nidus. It is in room 177 on the main floor. That's the learning center. There are tables set up in there. So it's kind of cafeteria style. If you are a special person and you know you're a special person because you have something written on the back of your card because you are allergic to gluten or other things, then your lunch is available based on what the instructions say. So we wanted to make sure that people who are vegetarian or vegan, etc., theirs didn't get sort of accidentally consumed by someone else. If you need a special lunch but don't have those instructions, come see me and I'll make sure that you see the right staff person. So we just separated those things out. There, in addition to the tables in 177, you are also encouraged, welcome to go eat in the library, which is 176 across the hall. That's where the posters are. So there's some tables set up there. There also are some nice tables outside. I have not poked my head outside this morning to know. I looked at radar. It didn't look like it was raining. But if you want to head outside and get some fresh air, you're also welcome to do that. There is one additional little thing at lunch today that we're going to do. And Marina, do you want to tell us about where and when that is?
I'm just going to get caught on my earrings. Don't wear earrings if you're wearing a mask. Or don't wear a mask if you're wearing earrings. Hi, everybody. So we have about 12:45. I'm going to be coming back in here and I invite any of you that are in the mood to sit some more and hear some more and share some more, to come back to hear about this project in the Upper Missouri River Basin. Nathan Edwards knows all about it, others here, but we have the opportunity to do some research around that, and I'm really hoping to get all of your creative input on that. And so I'll start out with just a little hopefully quick presentation on that project, and then a roundtable dialogue on that. So that'll be starting about 12:45.
Yeah, so that is option one. Option two is you can take the full hour and a half to visit if you would so choose. Our presentations this afternoon will resume in this room at 1:30. And and for those online, 1:30 Eastern is when we will resume the broadcast. So this building on main campus where I am, there's lots of traffic from High Street. And so we do have issues with laptops disappearing from time to time. This building is relatively remote from the rest of campus and does not get a lot of passers through. And the staff here pretty much knows everyone except when there's a conference going on. So I would say it's, relatively safe, although I'm not going to write a check if your laptop walks away. So there are also some people who have offices in this building who, if you wanted to, or if you want to leave your stuff with a staff person in the main office or throw it in someone's car or whatever, you can also do those things if you don't want to carry it around. Yeah, so Aaron is available to help you if you want to, yeah.